Right. So, yes, I've been talking for way too often on way too many things. The talk I'm going to give today is about running tests from something like Jenkins against clusters of multiple machines. So very similar to the previous two talks, but fortunately different, so I'm not going to repeat anything either of those speakers said. But the reason this is relevant to me is because we're working on deploying cluster software. OpenStack itself is one of the more complex clusters out there because it's kind of got the union of requirements of every single cluster product. It does storage and it does compute. It's sensitive to hardware irregularities. It's sensitive to the layout of your switch and your network topology. And people often use it to deploy cluster software on top of OpenStack itself. So if you can't get that right, there's no chance for the user workload to work properly. And the problem is testing. Unit tests, they're pretty simple, right? You pull together your test environment, you load the process, you run the tests. It doesn't actually do anything, it just tells you what you already knew, and it exits. Functional tests, though, where it starts to get much more interesting. And functional tests are, to my mind, the defining characteristic of them is that they will surprise you. They will tell you things that you didn't know because you'll find out that actually I/O latency can make your application run 100 times slower than you expected as soon as you have two processes trying to do something at once. Or that actually you're trying to push 5 gigabits a second. Am I hearing myself speak or someone else speak? Sorry, it's really distracting. If you try and push 5 gigabits of data through a 1 gig network connection between two servers, you'll find it out if you've got two physical servers involved. So a functional test that does that's valuable. You won't find it out if you're on one single machine unless you go and deliberately set up bandwidth limits between inter-process communications. So it's much easier to find out about real-world impact on your application if you have tests that are reflective of real-world deployment scenarios. And I'm trying to remember why I put that like that. So the question is, if you've got a Jenkins environment, Jenkins has two basic ways of deploying nodes. You can either say, here's a machine, I'm going to run the Jenkins slave agent on it, and Jenkins will then say, hey, that's a machine, I can run tests there. And you can tell it some concurrency. Run one worker there, run two workers, and you assume there's no interaction between your tests and everything's well isolated and other lies that you'd like to tell small children. But as soon as you actually try and run two machines, Jenkins has no way to model this. So what you end up doing is saying, I'm going to install, let's just for argument's sake say a 5-node cluster, and on one of those machines, I run the Jenkins agent, and I have a static config file there that says these are the other 4 machines, and my SSH keys to connect to them. And this is actually very inflexible. If you're in a cloud environment, you can spin up new nodes dynamically. This is the second way that Jenkins can provision nodes. You can say, here's a plugin, here are my credentials to Rackspace, create test nodes as needed, and it will spawn them, SSH in, and run the agent. But you're not getting a cluster here, you're getting one machine. Do you want to put your credentials to Rackspace, which can spend thousands of dollars, in the test node, where test code could read those credentials and then spawn as many nodes as it wants? It would work, but it's going to constrain you to a very small set of people that you'll be wanting to trust that when they author the code. And if you've got an organization like OpenStack where we're trying to allow anybody to contribute, you need to get away from such things that restrict your organizational growth. You need to separate out, these are the things that we need to trust and restrict from these are the things that anybody can do. It should be unprivileged. And OpenStack, I forget the figures, what is it, 400 slaves a day or something you chew through? More? So OpenStack goes through lots and lots and lots of Jenkins slaves for two reasons. One, it runs lots of tests in parallel, so it needs a lot of slaves actually active. Up to 50 or 100 offhand, no, that's jobs, not slaves, so times by 5, up to 200 or something active at once.
It's like 350 active at once.
Okay, I'm behind in the figures. 350 at once. Fortunately, I've got experts here to correct me. But then they only get used once because resetting a test OpenStack slave to a known good state is actually pretty hard. The test environment makes a lot of changes to things like VM settings, write back cache, networking. And if you want to check that that script that actually is going to make these changes works, you need to undo all of them. And the easiest way to do that is just use a snapshot and restore to the snapshot. So we need to solve this problem, and we've almost solved it. And so in this talk, I'm going to talk about how we've almost solved it. And hopefully that'll be useful for you. So in principle, the ideal solution is you use an infrastructure as a service cloud, and you say, hey, give me 4 or 5 test machines. And you do that straight from Jenkins, maybe. So you have a plugin that instead of asking for 1 machine and putting the agent on 1, asks for 5 and puts the agent on 1, and does SSH keys so they can all talk to each other and sets up that config file for you. That might be pretty nice. Couple of problems with it. One, if it's in a private environment, you're probably going to end up oversubscribing. And for test results, fidelity is key. If you're trying to do load testing or performance testing, the worst thing you can possibly do is to run 2 load tests at once on the same hardware, because neither of them will tell you anything useful about real-world behavior. The reason I keep looking this way is I didn't set this to mirror, I'm sorry.
Can I just ask, what sort of functional tests are you talking about, and how, what sort of situations do you get into where it doesn't work just on one node?
Okay, so the question is, what sort of functional tests am I talking about, and when does one node stop being relevant? Okay, so I'll answer the one node thing first. Okay, if you start with physical hardware, a physical machine might have 2 spinning disks, so you've got 2 heads that can seek at once, and imagine you're testing something like Swift, which is doing lots and lots of I/O, and you're testing to see whether its performance is constant, or at least hasn't regressed. 1 machine per test run, a one-to-one relationship will work there, but it won't tell you whether it scales. And if you then say, okay, I want to see that at 4 machines I get 3.5 times or better the performance that I did at 1. 1 machine can never tell you that by definition. If you say, let's scale that machine up by putting 8 disks rather than 2 in the 1 machine, well, you're actually storing through the same kernel, you're running through the same file system interlock. For example, Postgres found a shared kernel lock on ftrunk when they were doing a whole bunch of scaling performance work that they didn't expect. And it was cross-file, like all files were going through the same lock, I believe was the situation. It's like, okay, hang on. So can you be confident that your results that say everything is terrible actually mean it's terrible, or equally that results that say it's great actually mean it's great if you're on 1 machine? And I contend that you can't. You've got near infinite bandwidth between test processes. That's unrealistic. You've got 0, or effectively 0 latency between test processes, unrealistic. Your disk I/O is running through 1 elevator seek, or whatever scheduler you're using to constrain it against your actual available back-end I/O. None of these things actually are really reflective of real-world environments. Second thing is, if you're testing something that requires a lot of memory, buying a big machine with 256 gig or 512 gig of memory is actually kind of expensive. And if what you're testing is how it behaves when you've got 100 nodes in a cluster, if each node needs 4 gig of RAM, you're going to run into real trouble very, very quickly doing that. So if you were doing Java test clusters or Hadoop or something like that, I'd be really worried about trying to get good results out of a single machine. Now, so that was why 1 machine won't do. What was the first part of the question?
What sort of functional tests?
Right, so I think I've actually covered both of them. Right. So in principle, though, so VMs get even more complex because VMs have all of the shared machine problems I just described, and they then have the problem that you've got a bunch of overhead between the VM and the hypervisor. So you may actually run into some of those scaling things earlier, or VMs, you may get cross-VM contention. So that's kind of tricky. And I'll talk about how we address both of those things for our particular use case. But this is kind of like the ideal world. And ideally, you just run up an infrastructure as a service cloud, OpenStack, for example, and you say, right, my tests need 5 VMs, Jenkins will do it, it's great. We can't do that for our tests today. Many tests could do that. The reason we can't do it for our tests is that we're testing OpenStack itself. And OpenStack, as an IaaS provider, does things like anti-spoofing to stop VMs pretending to be other VMs. But an HA network service setup actually needs to do that, because you need to be able to move the virtual IP around. You need to be able to spoof traffic. In principle, we can do a whole bunch of changes to OpenStack to make this policy-driven, so that some users could do it under some circumstances for some IPs, and then tie that all together, and then wait for our cloud providers that provide our testing resources to deploy that version of OpenStack and turn on this feature, which might be optional. And at that point, we should have had this working 3 years ago. So we wanted to deliver something now, rather than this long arc. But we might come back to that. We also need PXE boot on the machines, and at the moment, OpenStack doesn't have PXE boot as a concept for the VMs it deploys. It's a local machine, do your thing. That one's probably easier to solve. But that only talks about VMs. There's the other layers. We want to talk about how we deploy into physical machines. And for that, we need actually to be dealing with the IPMI or ILO DRAC sort of thing. And is Nick still in the room? He is, yeah. So as Nick knows, having two different processes talking to one IPMI controller is not a good idea. They're going to trample on each other. Exactly. So if we used an IaaS cloud to, like Nova, if we used Nova to deploy physical machines and ran our tests on those in a cluster of 4 or 5, because we're testing OpenStack itself, both the cloud we use to deploy the test environment and the test environment are both going to be turning those machines on and off, and I can't imagine things being smooth sailing. It just doesn't seem like a good idea. So we thought, let's consider this. You've got a dynamic thing, the slaves that come into Jenkins, created once, thrown away, and you've got the persistent resources. The physical machines are persistent resources, and if we've got VMs that we're going to use for testing, because we want to make sure we don't oversubscribe, we want very predictable behavior, we want them isolated in a very static way, we'll just set these up as static test environments, and we'll create a broker. So our dynamic slave comes along, test starts, it says, give me a test environment. The broker comes back and says, here's a test environment, and you run your test, and if the test crashes, the environment gets freed. If the broker crashes, the environment gets freed. If anything goes wrong, the environment gets freed. It's available for the next one. From a Jenkins point of view, we're modeling just single tests. We're not needing to worry at the Jenkins level about having multiple slaves. And by having the resources set up in advance, we don't need to worry about permissions. As the author of code running in that test, I have no ability to ask about credentials. I don't need to know root on any other machines. I don't need anything else. I do get access to the IPMI if I'm doing a bare metal test. I'll come back to who gets to test what where later. So the Git URL there has all of the stuff for OOO CI. So it's not OOO itself, but it's the scripts around OOO that are related to doing CI. Liz here has been doing a lot of work in that repository, and it's got this client and broker, which are really very simple, and it's a Gearman-based thing, so we basically had to write, 100 lines of Python on each side, just glue code. So each test environment, and it doesn't run in the environment, for each test environment that we want to be able to hand out, we run a worker that advertises the test environment as being available. And it does that by advertising a function to Gearman. Who doesn't know Gearman? Okay, right. Less hands than I expected. There's lots of Gearman knowledgeable folk here. Cool. So Gearman is it's a very, very lightweight message bus. Essentially, you connect to it. It's a peer-to-peer protocol, and you can say, hey, I'm able to serve a function, and you just give it your own name. And when something comes in that wants to have that function run for it, the Gear server, the daemon, asks which of the people that registered are actually ready to serve something. And then they can say, hey, yes, I really am here, and you go forward from there. So what the worker does is if the worker is currently in use, it doesn't answer that second question. It registers when it starts up. And if it's idle, it will then say, yes, I can work. Otherwise, it does nothing. So it doesn't do kind of overlap to concurrency. It's just a single process. It's either being used by somebody or not. But we needed to be able to tell if the test run crashes, and Gearman only tells you if the function you're running crashes. It doesn't tell you if the person who requested it has gone away. So the way we solved that was we run two functions. As a client who wants a test environment, I connect to Gearman, I say, I'm advertising, and it creates a UID, just a random function name. It then asks for the test environment. The test environment, when it's asked for the test environment, it passes that UID as a callback. So the test environment, to actually run, it connects back through Gear to the client and says, oh, by the way, here's the details for the environment. And it does that, rather than sending a result back, it does that by invoking that UID function. So you have a equals B equals A, and Gearman, if either of them break, will tell the person who initiated the call that the other side broke. So we get rid of all race conditions by doing this. We have a timeout if you connect, and there's only one condition where we wouldn't find out, which is where we connect and they connect back, but the client's already gone away. So we handle that one by a 30-second timeout. This means we don't need a sort of distributed lock manager, we don't need persistent locks, we don't need sysadmins to ever go in and clean up a test environment. As long as the worker process, which has, tiny footprint, is still running, it's going to work correctly. That's our theory. This is the client calls the worker and passes in its callback, and when the worker calls the client, it passes in a JSON dict that has all the details for the test environment. For a VM, it will have the VM host, it will have the VM names. For physical machines, it will have the IPMI details and the MAC addresses of the machines and how much memory, disk, and so on they've got. That's also completely generic. There's nothing in that code that is specific to our environment, and that's deliberate. We haven't repackaged it yet, but we'll come back to that. So if we're testing Nova Bare Metal or Ironic, we've got two basic scenarios. One is we trust the code that we're testing because it's gone through code review, where no one has snuck in, or if they have snuck in, they have collaborated with two core reviewers to sneak in malicious code that will attack the firmware in the machine or do something, or make it melt, or whatever it is they choose to do.
So well done.
Look, if they can sneak that in and have no one notice, congratulations. But the other scenario is the more common scenario. People put up a patch and it needs to get reviewed, and they put up a patch and it needs to get reviewed. And if they put up a patch and delete it, no one may notice it. So they have a fairly large opportunity. It would be audited, but audited and noticed are two different things, to sneak malicious code up. So we only run that untrusted code in VMs. And so what we have there is we have some VMs, probably 2 or 3. We don't know the exact number yet because we haven't got to that point in the what Nova Bare Metal or Ironic functional tests will need. But they'll be set to boot from PXE. There's a Versh Power Manager, so they'll get access to talk to Versh over SSH to the hypervisor host. They'll be set on a little isolated bridge, so if they PXE or whatever, the rest of the world won't notice. And requests from that will be forwarded back to the supplied address of the slave at the time it's connecting. If it's trusted code, then you get the IPMI details, and because you're going to be on a shared LAN at that point, because all the physical machines are plugged into a small set of physical switches, and we didn't want to go crazy with VLANs, we're going to supply to the test script a network range that it should use. So we don't have to gamble on them not colliding on IP addresses. I should talk about definitions. Who does not know what Nova or Ironic is? Okay, right, so that slide probably didn't make as much sense as it could have. This is a bring your own adventure talk. Nova is an API for getting machines from a hypervisor. So you can use Nova to get physical machines with Nova Bare Metal or Ironic. You can use it to get virtual machines with KVM or Zen, and you can use it to get containers with LXC or Docker. So the context here is specifically about physical machines. We're testing the code path that's used to provision physical machines, and that code path can be tested with some caveats on virtual machines, which is why the untrusted path using VMs is still a valid test scenario. It won't catch everything, but it will catch a large chunk of the things that can go wrong. O is OpenStack on OpenStack. It's our deployment project for deploying OpenStack using Nova to deploy the machines that will then host Nova instances to run VMs. And so we have all of the testing caveats that Nova Bare Metal or Ironic do, but we also have additional requirements in that we need machines that are capable themselves of being hypervisors. So if you were to try and test this against a QEMU machine, it's not going to work very well because running an emulated hypervisor inside an emulated hypervisor is extremely slow. Running an emulated hypervisor inside KVM is moderately slow and still slow enough that it's potentially a big deal for us. So one of the early issues we tried to run like 3 QEMU VMs inside the KVM VM that we got from Rackspace or HP Cloud. After half an hour waiting for it to boot, we moved on. So what we do now is we get a VM that's a KVM VM, but we can turn on nested KVM if we want to. But the key thing is the VMs we get are actual KVM VMs. They're not QEMU VMs within a KVM VM. So they're right down at the lowest level we can get without running directly on the metal. So for the untrusted code path for us, we need a VM to use as seed. That's how we start our deployment process. We create an image that we can run on a VM that can do the install, and then we bootstrap up from that. And we need a bunch of VMs to actually deploy to. And again, we need virtual access to the host, and we also need to be able to supply that seed VM. We need to be able to copy it up so it can be run in the first place. Because when we begin, there's no infrastructure other than a basic shell and virsh. Trusted code, exactly the same, except rather than a bunch of VMs for the bare metal machines, we get a bunch of physical machines for the bare metal machines. And we've got a community cloud contributed to OpenStack that we're using for this. We've got, I think, 50 machines from HP and 25 machines coming online from Red Hat at the moment, and several other vendors who have expressed interest and are currently going through the internal process of getting that turned from, yes, we want to help, into, and here are the details to do stuff in our data center. The OOO tests, though, are kind of slow because we have to build an image, load it onto the seed VM, then we have to build images for the other machines we're deploying and load them onto those machines. And servers take 10 minutes to do a power on self-test. And if we have to do 2 of those because we copy, deploy, reboot into the final image, that's 20 minutes minimum, and I haven't run any interesting code yet. I've just waited for machines to turn on. So what we want to do, once we've got this actually working reliably, is to split our tests up. And instead of do the seed, then do the infrastructure cloud in an HA setup, and then do the end user cloud, and then test workloads against that. So that's 3 clouds. 3 clouds? Seed, undercloud, overcloud, end user, 3 clouds. We want to keep the tested results from our previous tests. We say, we know this works. It's what's landed in trunk. And have it sitting there ready to hand out as a test cluster. So we can do one test that does the seed and stops after it manages to deploy something with the seed. We can do another test that starts with a running seed. So we'll have a pool of 20 running seeds, and we can just say, hey, give us a seed. And then you skip that whole first part of the process, and you just deploy the next release, the tip, that you're testing against the running seed. And you do another one that goes against a running bare metal undercloud. And possibly even one that takes a fully deployed cloud and just tries to deploy the next step up from it. And we can pre-prepare all of these environments. This should let us go from a serial workload with many different test runs running at once to a parallel workload with many different copies of those running at once. The only problem is that there's a chance, if there is an incompatibility, that would be caught if you ran the same code for every step, but not caught if you run the old code as what you're deploying against, that we could let a bug through. That's what the thread the needle reference there is to. It's Sean Daig's terminology for this, and he really doesn't like that risk. I think he'll like that risk less than the delay it takes to test everything end to end, but we'll see. Right, so the broker code, as I said, it's 2 files. Yeah, there's a question. I almost did a whole talk in response to my last question.
Just with that thread the needle, could you address that just by occasionally doing an out of band test the whole?
Yeah, no, so the problem is that if you thread the needle and you introduce a thing that fails 1 time in 100, that's fine. Pick that up 24 hours later, fix it, not a huge deal. Don't comment. If you introduce something that fails 99 times out of 100, you've just broken something that's got 50 concurrent tests all trying to go into the gate right now, and as soon as you update those last known goods so that this thing activates, everything's going to grind to a halt until you analyze, figure it, revert it out. And we've got so many commits landing at once that we're already doing speculative pipeline commits for stuff. So if it eventuates, it's actually a really big deal. And even a 1% failure thing is also, in aggregate, a big deal. So in both cases, we'd really rather not have it. But there's actually cases both ways, right? So you want to make sure you work cross-version as well. You kind of want to do both all the time. We need more machines. Would anyone like to contribute some machines to OpenStack?
I have no budget.
All right, so to be able to reuse the broker, we should probably package it up in pip so you can pip install it. But it really is like 2 100-line files in Python. It's trivial. We don't include the business logic. You need to create a JSON file that describes your environment, and you need to actually make your environments. You need to either set up a bunch of VMs or have physical machines and, bunch them up however you want to. Thinking about Beaker stuff here, one thing you could do is have one environment per machine, and then a test that wants 4 machines could ask for 4 separate environments.
There's actually a thing called the Jenkins Beaker builder, which is submitting Beaker jobs from Jenkins.
Right. Yeah.
Yeah,
So I thought about going and digging into Beacon and trying to pull stuff out, but it's such a big monolithic. I was like, this will be quicker, and I think it has been. So on the one side, I cringe, on the other side, I think it was the right decision.
Yes, this Beaker's got a lot of complexity in the inventories.
The 2 is a typo. It's not actually environment squared or anything silly like that. The way we deploy this ourselves is that we use Heat to deploy the machines that will host the VMs for our test environments. And we have a script in those VMs that sets up, it interrogates the machine to say, hey, how big are you? 24 cores, 64 gig of RAM. Okay, the environments I've been asked to create all 2 CPU, 4 gig. I'll divide that out. I can get 6 environments. No, yes, 6 environments will fit. Great. And then it creates that many VMs, creates a JSON file for each, and spawns 1 worker per JSON file to register them all with Gearman. Heat so we have a stock image that will do that on any machine. You run it on the machine, you get that many environments out. And it's parameterized by passing metadata into Heat to say where the Gearman server is. So it's pretty much run 1 Heat stack create command done to set it up, or to rebuild the entire thing if something goes wrong or if you've got a new version to deploy. So fully automated, automate all the things. And we put the client into so Jim mentioned earlier today the node pool, which takes the script, runs it, and saves a snapshot of the image to use for testing. So you can quickly deploy a well-known starting point. We've got a different script that's run by node pool to create the images for running against this sort of environment. And we have the client script embedded in that image. And all it needs is the Gearman D address to be able to connect up and have it all hooked together. We haven't figured out how we put that in to that at runtime rather than when we build the node pool image. Maybe it's a wrong question and we should talk. Right. Did I run too fast? I probably did. Questions? See, this is why I shouldn't answer the questions as I go, because come on, surely someone's got something to ask.
So, when you said triple O, do you intend to have it that way even for production, as in like user VMs? Are they going to be deployed on top of other VMs?
So for triple O for production, so if I go back to this slide here, the untrusted code path is what someone who is developing triple O would do. On their local machine, they can set up enough VMs, or even on a couple of machines, enough VMs to experiment with and see how the basic flow happens. But for production, the trusted code path is actually exactly what will happen in production. You'll start with a VM, and you'll start with nothing, you'll create a disk image, and you'll run that as a VM, manually configured with Versh. By manually, I mean you run a script of ours rather than by using an API to do it. Then you'll use APIs against that VM running VM cloud to deploy to physical bare metal. And that will deploy your actual infrastructure. It will deploy the infrastructure as a cloud, the bare metal infrastructure as a cloud infrastructure, Keystone, Swift, Glance, whatever you need as your infrastructure management layer, monitoring, reporting servers, firewalls, the lot. Then you talk to that to deploy your workload cloud, which is your KVM hypervisor cloud. And so that will also deploy onto bare metal, but we deployed onto bare metal by the infrastructure as a service cloud. At this point, you've turned off that initial VM. It's not there anymore. It was only used to get up and going, because we didn't want to have two different deployment mechanisms for deploying to physical machines. So we have one mechanism all the way through. The only thing we need to special case is how you bring up that first VM.
And the seed VM, is it cloud to create the other VM images, or
Yeah.
is it copy?
The seed VM, we create the image using Disk Image Builder, and then we just copy it into place in varlib, libvirt, images, blah, and then we do verse start of that image. What's inside that VM is a fully functional OpenStack bare metal cloud with all the bells and whistles. And so the next thing we do is we do ironic create, and we create the physical machines that we're going to register the physical machines with ironic, and then or Nova bare metal, whichever one you're using, and then we do Nova boot, or actually we do heat stack create, because we have a stack that describes how to run OpenStack, and off you go.
It's OpenStack's all the way down.
Well, it is, because after we move off the seed, the infrastructure, the bare metal cloud, has registered with itself the machines it's deployed on.
Yeah.
So the only reason that works is because there are two machines there, a minimum of two, that can deploy to bare metal, so they can deploy each other for upgrades. So if you were to try and do a graph describing what machines deploy by what machine, it's got cycles, right? There is no bottom.
Have you read Greg Egan's Permutation C?
I think so.
Yes.
It rings a strong bell.
That just reminded me of that. Question in time, it's perfect.
Doubters.
Thank you.
You're welcome.